cyclohexane with the question above with the tosylate and the iodine. So now you have the answers of this cyclohexane, but could you also put both of those on a dash and that'll be the same answer?
Technically, in a way, yes, because you can rotate the molecule, but that was more something that Dr. Yermain would do.
Okay.
Dr. West is not really going to do that. Yeah.
And those are considered what, the same molecule or not an enantiomer?
They're going to be the same exact molecule because you're just flipping them around.
Okay.
And that's it. Okay, any other questions on protecting groups? We're good? We're ready for the new stuff?
Yeah.
Okay, yeah. We're a little tired. That's okay. Okay. Next topic was oxidation. We didn't talk about this one, but we actually did talk about the definition of oxidation. So really quickly, how do we know we're doing a reduction? Say that again? Exactly. So we know that oxidation is the complete opposite. So what's oxidation? How do we know we're doing it?
No.
We're increasing the bonds, exactly.
Fill this out prior to
This?
the oxidized. Never mind.
Yeah, because they're quite long. So
Okay.
to actually make it legible for you guys,
Right,
I try to do it
got it.
beforehand. So yeah, it's for your own benefit at the end. But okay, oxidation. We know we're just increasing the amount of bonds between carbon and oxygen. Reduction, the complete opposite. Now, before we talk about the actual reactions, there's a few reagents that you guys should memorize, and please start writing them down. They're very important. Now, similar to what we saw in reductions, we have two main categories, weak and strong. Now, in this case, we are not really going to talk about the reactivity of carbonyls and any of that. You just have to memorize just those two lists, weak and strong. Now, the easiest one to memorize, of course, is going to be the weak one. And I will keep in mind PCC. You use that one a lot. And then for the strong oxidizing agents, notice how they all have a high content of oxygen. So as long as you memorize the weak ones, and then if you see a high content of oxygen, that should be strong. Now, the names Jones and Soren's reagent, that's more for Dr. Roche students. He tends to use the actual names. For you guys, I haven't seen him use it, but just in case, there it is. So DMSO, that's your Soren's reagent. Jones reagent is the very first one of the strong ones. So again, this part is just memorizing. Okay, now let's talk about the actual change. Now, as we know, oxidation, we go from some sort of alcohol group to some sort of carbonyl group. And actually, let me zoom in first so you guys can actually finish writing down your notes. So just let me know when you guys are done. Yes. And you might see that one in the book if you guys ever read the book. But again, you don't really need it.
I was talking to my friend about Roche, who he took the test also. Is it very hard to understand him?
Dr. Roche?
Yeah,
Like, do you mean because of the accent?
yeah,
No.
it's not.
Is that a C or a G? H2.
H2CR04. Next one, Na2CR207. Next one, CR03. And last one, KMNO4. Not really. No.
I heard he's here to exam. That's true. It's true.
Yeah. There's like a little trend, like Dr. Roche's exams tend to be slightly easier, at least for the first part. And then for the second part, that's when he complicates it a little bit more. But as long as you know your stuff, you should be able to figure it out. So yeah, but I mean, Dr. Roche does something that Dr. West doesn't do, which is the presentations exactly. So you would have to come to the podium and explain how you solved certain questions. Yeah, so most people don't want to do that. So that's why they choose Dr. West if they know that. So either way, are we good with the list? Do we need a few more minutes? Oh,
Just to reiterate, because I missed what you were saying, you said an oxidation is happening if the carbon oxygen bond is increasing. So
Yes.
it's not like a single bond,
if you're in,
double bond.
exactly. Okay, now. Just let me know when you guys are done. But for oxidations, we are not gonna be talking about the mechanism like we did with reductions. We just have to know to identify the actual transformation between the molecules. So in this case, if we go up, for the very first one, let's identify what kind of molecule we're starting with. We know it's an alcohol, but what's the degree?
Primary.
It's a primary alcohol. Okay, now the aldehyde is just gonna be an intermediate whenever you use a strong oxidizing agent. That's the main part. This is gonna be for strong because the aldehyde is just intermediate. At the end, the final product is gonna be the creation of, what's the name of that functional group? Carboxylic acid, exactly. Now, very similar in this case. What kind of alcohol is this?
Primary.
Primary as well. Now, we're stopping at the aldehyde. It's gonna be a weak reducing agent. Sorry, weak oxidizing agent. Oops. And now, again, very similar. Very last one. What is it? What kind of alcohol?
Second.
Secondary alcohol. We have two R groups. And we're always gonna end up creating a ketone, okay? It doesn't matter if you're using a weak or a strong oxidizing agent. It's always gonna be the same exact product. So strong and weak. Exactly. So again, it's just identifying initial molecule and what's the final product. You have to see that transformation so you can know what kind of reagent you're using. Yes.
Why is a ketone a strong weak?
Because at the end, no matter what happens, notice that, for example, in our primary alcohols, we only have one R group, and at the very end, it's over here. Same process whenever we use the weak one. We're retaining the R groups from the alcohol groups. So in this case, if we have two R groups for our secondary, we're only gonna have two bonds in there. If we add more or less, we would be breaking the octet. Or if that means that, for example, if you end up with an aldehyde, that means that you're not starting with a secondary alcohol. You're always preserving the R groups from that alcohol. So does that make more sense? Are we confused? Okay, if we're confused. Okay, what is that?
What about tertiary alcohol?
We're not gonna be dealing with tertiary alcohols, not at all. So this one is gonna be pretty simple, only primary and secondary alcohol. Okay, and let me zoom out. Okay. So far, questions on oxidation? We're good? We're good, okay. So again, this is just plain memorization, and actually for probably the rest of the class, it's gonna be mostly based on memorization.
Like the rest of the semester?
Yeah, because from this point until the very end, we're gonna be doing a lot of reactions, okay? And once we get actually to the very last chapters, you're gonna see that some of the reagents are gonna be the same, but they're gonna have different products depending on what molecule you're starting with. So what I like to recommend my students to do is to start making a little list of the reagents as you go. So you don't have to show the mechanism or anything, just show very similar to what we saw in here. Initial molecule, the kind of reagent we're using, final product. So you can use it as a little cheat sheet as you get closer to the actual exam and for the final. Okay, let's move on to the next aspect of the chapter. Okay, so from now on, we're gonna be talking a lot about ethers and epoxides. In this case, we're gonna start with our normal ethers. Now, you guys are gonna learn how to make and how to break them, okay? So let's start with how to make them, which is actually gonna be through this reaction, Williamson ether synthesis, or like I just like to call it, is just the West reaction. It's not like your professor, it doesn't have a T, but still very similar. Now, this one actually, you guys probably learned it in Orgo 1. Does it kind of look familiar? Not at all? Not at all? Okay, that's okay. So first of all, let's see what reagents we're starting with. So first of all, we have an alcohol group. Really quickly, what's the name of that alcohol?
Primary.
It's a primary,
Oh,
but what's the
name?
IUPAC name?
Methanol.
Methanol, it's ethanol. We have two carbons in there. Okay, we have our ethanol. Now, first reagent is gonna be NaOH. What kind of reagent is that?
Strong acid.
Strong base in this case,
I thought,
remember. Ionic
alcohol.
bond goes away. You're left with a pretty good base or nucleophile. In this case, it's just gonna act like a base. And now, next reagent we see is gonna be a carbon chain with the X. What does the X represent? What do you say over here? It's a halogen. Yes, whenever you see an X in all of the handouts, it's just a halogen.
So staying. Specific.
Yes, you can use anything. So this is called your alkyl halide. Now, the two main parts of this reaction are actually little reactions that you know. Very first one is always going to be an acid-base reaction. So pretty simple. We know that one. The next step and final step is going to be an SN2 reaction, which we're also very familiar with. So far, questions on that? We're good so far?
How'd you get to that? So, like,
Let's see the full mechanism. Right now, we're just identifying what are the main reagents for this reaction to happen. Okay, now. So actually, let me show you stereochemistry in this case.
could you write the 2 and then SN?
Oh, thank you. Okay. Okay, so very first step, we're just gonna focus on our ethanol and that hydroxide ion. So if it's an acid-base reaction, we know that the base is just gonna be taking away that hydrogen. So you deprotonate that alcohol group. How do we call deprotonated alcohol? Alkoxide, exactly. More specifically, in this case, it's gonna be ethoxide. That's representing the 2 carbons. Et represents the 2. Okay, now. So far, we're not altering this stereochemistry. We just took away that hydrogen, that's it. Now, once we have our ethoxide, next reagent is gonna be with an alkyl halide, yes. What do you mean 2 negative sides? This is just an oxygen with 1 negative charge. Yeah, sorry again, my handwriting is a little funky, so it's okay. Okay, very next step, SN2. The alkoxide, what kind of reagent is that?
A good nucleophile.
It's a good nucleophile, exactly. And we're reacting with an alkyl halide, so that's why we're doing an SN2 reaction at this point. So we know that this is when we do the backside attack, so we have to keep that in mind because SN2 reactions are always going to flip the stereochemistry. So lumpers in the nucleophile, attack the carbon, you kick off your leaving group, and that means that we are going from a dash bond to, to a wedge in this case.
Where did the alkyl halide come from? Just one of the,
It's just an extra
reactants.
reagent that you have.
Okay.
You always need 2 main components for this reaction. Base, alkyl halide. That's how you know you're doing this reaction.
why do you end in 2 wedges?
Because in the alkyl halide, we have a dash. So to represent that change of stereochemistry, I have to show it some way. So in this case, the way that we're gonna do it is just by focusing on the bonds directly connected to that oxygen. So the one on the left is the blue one, the one that we originally started with. We're not changing that. But the next carbon chain, 1 and 2 carbons, are coming from the alkyl halide. And again, because it's SN2, I'm trying to show that stereochemistry change. So I know that the carbon that I attacked was with a dash with a halogen. So SN2 is gonna flip it to a wedge. So that's why we end up with 2 wedges at the very end.
Can you repeat that last part one more time? Like the last 4 sentences you said. So the 1 and 2 carbons goes to the 1 pink. So you're leaving the stereochemistry of the blue one,
Yes,
and you're flipping the stereochemistry of the pink one.
of the pink one, because that's the alkyl halide. That's the reagent
And that's
that
the
participated in
SN2.
SN2. Exactly.
But I thought when you're leaving group leads, the bond, the wedged bond breaks and the electrons go to the alkyl, go to the halide.
So the electrons are going to the halogen, yes. So in this case, we still have our little X minus, and there is just floating around. It's not by product. We don't focus on that. Now, in this case,
Oh,
this
you still
molecule.
have the- Okay, got it.
Mhm. So if we draw the same molecule but with two dashes instead, it's the same exact thing. It's just flipped around. But really quickly, we formed an ether, and we know how to name ether. So what's the name of that molecule?
Okay.
Beautiful, you got it. So yeah, this is a diethyl ether. Because right now we're just naming it based on the parent chain as the ether. So remember, if the parent chain is the ether, we just end with ether. If it's a substituent, what kind of suffix do we use? Oxy, exactly. Yes.
How do we know that the alkyl halide is wedged? Will it be wedged when he gives it to us?
He's gonna give it to you. Yeah.
Wedged, okay.
Yes. If everything is planar, then you don't have to show stereochemistry. You just have to show the connections, and that's it.
Okay.
Yes. I just put it so you guys would know the flip. I just want you to remind you that SN2 is gonna flip the stereochemistry. Yeah, so originally the alkyl halide was a dash. Once we do SN2, that's when we flip it, only once. Again, technically the wedge and the dash from the alcohol and the alkyl halide, they were provided at the very beginning. I just forgot to show it in the handout. Yes.
Sorry, one more thing. Is there any, I'm being very picky, but your notes help so much. Is there any way you could turn the wedge into pink? Just so that it's color coded with or the dash into pink, just so that it's color coded.
Oh, yeah.
Sorry, thank you.
No, don't worry. I left the color code, so that makes me
No,
happy.
it really helps when you, with the other handout, everything's
Yeah.
color coded, it's so easy to follow.
Yeah, I love color coding, so. Yeah, you can make those requests. I'm gonna be very happy to do that. Okay, now. Do we have any questions on the reaction? Pretty simple. We know the two main steps. We just combine them together and that's it. Okay, are we ready for an example? Okay, now this time you guys have to note the same reaction, but intermolecularly. So intermolecular reactions are always going to give you some sort of cyclic structure. So again, same steps. First step, acid-base reaction. Then we do our SN2 reaction. Now, because it's an intermolecular reaction, this time we have our initial molecule with the alcohol and the halogen, okay? And then the only reagent that you're given is just that base. That's the one that's gonna kickstart the reaction, basically. Okay, so again, very similar. First one, we do our acid-base reaction. Sodium goes away. We are left with a pretty good base that takes away that hydrogen. And now we form our alkoxide. And again, right now, I'm not messing around with stereochemistry. So this is my little alkoxide. And there's my X. Remember, the X just represents any halogens, chlorine, bromine, any of those. Now, at this point, we do have our good nucleophile and our alkyl halide. So in this case, we don't have anything on the arrow, okay? Everything's provided within the same molecule. So this is the point when we do SN2. So we know that nucleophile does the backside attack and kick out that halogen. Now, the next part, I'm going to show it in little transition steps, so we all follow what's going on in here. So in this case, I still have that oxygen. I'm going to be breaking that bond with a halogen. And because of the nucleophilic attack, I'm making that new bond to the carbon. So technically, my product is going to look like this. But no, the molecule is a little funky. So we're going to be rotating the single bond. So it's less sterically hindered. So that bond rotates. Exactly. So now everything is going to be way better. And that's how we end up with that final molecule. This is your final product. Yes. In this case, it's going to be assumed that you guys can rotate the molecules as you please whenever it's single bonds. So that's why I like to show it in little steps. So because before, when I just showed the alkoxide to the very end, most people got confused. So that's why you get the little transition steps. So you see what's going on.
So this wouldn't work with, more than one bond, like if there was already a pi bond within the structure. It would.
Yeah, no, you're never gonna see pi bonds in this case for this reaction, all single bonds, yeah. So, okay,
And then you have the halide as a byproduct.
we just have X minus floating around. Okay, at this point, this one, it's a cyclic ethers, right? Now, more specifically, this is a special kind of ethers. Why? Because we have that little triangle shaped ether. So whenever we have one oxygen with two carbons only, this specifically is just going to be called an epoxide instead of just an ether. Okay.
So when you have one oxygen connected to two carbons,
Yes. In this case, we have that oxygen and those two carbons at the bottom, that's composing the ring. So again, members of the ring, one oxygen, two carbons, epoxide. Now we're going to be talking a lot about epoxides later on in the chapter, but we know how to make our normal ethers. Now we have to learn how to break them. Now, you have to know that normal ethers, the ones that are not an epoxide, are only going to be cleaved in acids. Only in acids. And they're always going to be stable or non-reactive with bases. Now, before we proceed with the actual mechanism, there's going to be a certain reactivity for your ether cleavage. Cleavage just means that you're breaking the bonds, and that's it. So the specific ranking is going to be tertiary. It's not going to be secondary. It's going to be primary and then secondary. Now, do I have any Roche students right now? No? Okay, that's good. Now, this ranking is only for Dr. West. So just in case for Dr. Roche, it's actually going to be 3, 2, 1. Don't ask me why the professors are using different rankings. It doesn't make sense. Yeah, I don't know. Like I've talked with Dr. Roche and he was like, no, it's 3, 2, 1. But then Dr. West's slides is like 3, 1, 2. So let's just focus to what we see on the PowerPoints and that's it. But still, like, I'm gonna try to ask him today, like, which ranking are you using? Either way. Okay. So this ranking right now, it doesn't make sense. So let's look at the mechanism first. So it makes sense. So in this case, I have a normal cyclic ether and HBr, what's that? It's a strong acid, exactly. So acid, that one is gonna produce a cleaving of that ether. So very first step is actually gonna be your acid-base reaction. Why specifically? Because we want to make that oxygen into a better leaving group so we can promote that cleaving. Now, oxygen just takes that hydrogen, and then we are still retaining that cyclic structure. We added one more bond, so that means that the oxygen has a positive charge now, so pretty good leaving group. And loading around in the molecule, I have Br minus, okay? This time that Br minus is gonna come into play into the actual reaction, so let's just keep it in mind. But after you make the oxygen a good leaving group, you're gonna be looking at those carbons adjacent to that oxygen. Now, you have to see the degree. That's where the ranking comes into play. So for the top carbon, what kind of carbon is that? Primary, secondary, or tertiary? Tertiary. So in this case, we have one R group, two R groups, and actually the connection to that oxygen is not going to count for the degree. So it's going to be secondary in this case. What about the bottom carbon?
primary.
Primary. Exactly. Remember, that connection between oxygen and carbon doesn't count as an R group. Okay. Okay, so in this case, we have the two rankings. So after that, you just have to look at what the actual pattern is, the actual trend. So what's going to be preferred to cleave, secondary or primary? Primary. So that means that I'm going to be cleaving the bonding here. So once I do that, that structure is going to be linear. So let's keep track of our carbons. Let's say this is 1, 2, 3, 4, and 5. And let's start drawing it out. We have a actually carbocation in carbon 1. Where's my thing? And I have that OH. This is 1, 2, 3, 4, and 5. Everything's planar.
But isn't there 6?
The 6th carbon is coming from carbon 5. So if we just label it this one as 6, this is your 6, and that's it. So remember, the counting the carbons, you can do it whatever way you want. This is not following like IUPAC rules or anything like that. So just do
Where is-
whatever is easier for you.
Where is the hydrogen? Oh, okay.
It's right there in the oxygen. So right now, everything is almost neutral. We just have that carbocation. Now, remember how in the very first step, we had that bromine minus just floating around? Exactly, it's gonna be attacking the carbocation. So bromine is gonna attack the carbocation and it's gonna get attached there. So at the very end, you're gonna have this guy. OH. And that's your final product. In this case, it's not the most stable carbon because if that was the case, we would have cleaved that secondary carbon. So- There you go. So yeah, that's the part that doesn't really make sense for acid cleavage. It would make more sense that you're cleaving always the most stable one, so it should be 3, 2, 1. But for some reason, for Dr. West, it's 3, 1, 2. But still, like, I'm gonna try to ask him to just reconfirm that. He might change it this semester, so.
Questions for like standardized places, no, like,
He doesn't use them from standardized places. He just takes them from the book.
so the book probably doesn't say 3, 1, 2, right?
It doesn't, oh, I think it does specify it.
So
I don't know.
then
I haven't checked the book in a while.
I feel like that we're gonna get it wrong, on test. The answers are gonna be according to the book, right?
Yeah, so,
I feel like if you asked me, it says 3, 1, 2, and I don't examine this 3, 2, 1.
yeah. I should give you the point.
Alright, I'll
And
ask.
I mean, in a way, the way that I try to make sense of it is that tertiary carbons, tertiary carbocations, SN1, you always prefer something that's really bulky. Now, between secondary and primary, secondary can work with either or. Primary can work better with SN2 because it's less bulky. So I try to make that, I think about SN1 and SN2, even though we're not really doing it here, but like, which is like the best preference for each of them versus tertiary, and then it's primary. Secondary, very last because it can work with either or, but that's the only way that I try to memorize that part. Okay, now, so far, questions on the mechanism? So far, we're following? Yes. And technically, you have 2 sets. And then in here, we still have 2. Then in the product, we also have 2. Okay. Okay, now we have the same exact reaction at the bottom. The only difference this time is that you're giving excess of the acid. How do you think that's going to alter the final product? What do you think is going to happen? So what's going to be the final molecule? What is it going to have instead?
To be
A double bromine.
Exactly, it's going to have a double bromine. Exactly, beautiful. So in this case, we know the actual mechanism, so I'm just gonna copy and paste it.
But how does it make OH leaving? Why does
It's the same mechanism.
It's the same exact mechanism, yes, but let me show you what's gonna happen in here. Okay, notability, we love it. Okay, so at this point, this was our normal product if we're only given 1 mole of the acid. If we have excess, that HBr is gonna be floating around again. And this time, we're only gonna focus on that oxygen again. We always focus on the oxygens first. What was the very first step? What kind of reaction?
acid base?
Acid base. So that oxygen is going to be protonated with the acid. So now we have OH with an extra hydrogen. So now we have a positive charge in that oxygen. Now it's a pretty good leaving group. And we have that bromine floating around in the reaction. So this part is going to be kind of like SN2. So that bromine is going to be attacking the carbon with a good leaving group, and that's how you kick out the leaving group, H2O. So at the very end, you have one bromine at the very end. And now on top, you have the second bromine from the second attack. Again, this is only happening because we have excess of the acid. And then technically your byproduct is going to be H2O. But again, this is going to be the main part. The molecule with two halogens. Okay, so far, questions on that? Yes. Okay, so again, quick shortcut in a way is just trying to memorize that order of reactivity so you know where it's going to be cleaved. And then if you only have 1 mole, the product needs to have alcohol and halogen. If you have excess, it's going to be pure halogen, and that's it.
I feel like this is way easier for the one.
Yes, it is. So yeah, actually, as we move on through the chapters, it's going to get a lot easier. Yeah. So the exams are also going to get a lot easier.
Yeah.
So yeah. Yeah, the first one, it's like the worst one, and then it gets progressively easier. Yes. Yeah, I didn't have like the best grade on my first one, and then I got like A's on the rest. So yeah.
Did you finish with that?
Yeah, that's why I have the job. Yeah. Okay.
I feel like Orgo 1, it was way more visualizing things.
It's because Dr. Jermaine did it really visual for you guys,
Really?
which is, it was nice, but it could confuse some students, but
So
Yeah.
it doesn't have to be-
Yeah.
he is, yeah. He draws like
did a good
so
job.
pretty, so pretty.
Yeah, he's a good part-time artist.
Yeah. No, yeah, he's really talented. So yeah.
Hobby art. Hobby art.
Okay. We have 9 minutes, so we're gonna keep going with the next concept. Which now we're getting into the epoxides more specifically. And yes, this part was already pre-filled out, so you can start writing your notes on that. Let me zoom out. Everyone is here. Okay, now epoxides, remember, those are the rings that have only 2 carbons and 1 oxygen. Is that gonna have a lot of ring strain? Epoxides specifically. What do we think?
One more time.
Do epoxides have a lot of ring strain?
Ring strain.
Yeah,
Yes.
they're both.
Yeah.
cis.
It's not because they're both
Okay,
cis.
so there's only-
The oxygen's electronegative, so it's more likely to pick up protons from its nearby surrounding.
And there's only 2.
Isn't it ideal to be a hexane ring and they're
Specifically, yes, that's from chapter 4 in Orgo 1. Remember.
Rings, one of those.
Yeah. So yeah, whenever you have any rings that have less than 6 members in it, there's gonna be a lot of ring strains. Why? Because you're not gonna be able to get into that chair conformation, so you're not getting the ideal angles. Okay, so that's going like back to the theory of sp3 and all of that. Now, we don't really have to focus on that, but the only reason why I mentioned that is because of that ring strain, that's really a lot. The epoxides are gonna be very reactive in both acids and bases. Remember, your normal cyclic ethers, they were reactive only in acids. Epoxides are gonna be cleaved in acids and bases. That's the main difference. That's why they're a little bit more special in this case.
What's a peroxy acid?
Peroxy acid, great question. So the same way that we made and break the the ethers, we're gonna do the same thing with epoxides. Now, peroxy acids, they're gonna be a new reagent for you guys to memorize. So in this case, you are only gonna have 2 main peroxy acids to remember. That's the drawn out molecules, and I want you to notice this. On both reagents, we have a CO3H group. So A way to remember peroxy acids is that as soon as you see CO3H, that should point you to a peroxy acid, okay? And again, usually he's not gonna provide you like with the actual drawn out structures, it's just gonna be in condensed formula. For Dr. Roche, he might draw it out, so yeah. Again, this part is just like memorizing. Now, let's talk about how to make our epoxides. So there's gonna be two main ways. One of them is gonna be with the peroxy acids, and it's actually pretty simple. It's gonna be with double bonds. So let me start drawing out this. Let's say that we have the structure, and let's use RCO3H. And again, I know it's a peroxy acid because I see CO3H. Okay, now, what you have to know about this reaction is that it's gonna be a thin addition. Now, we don't have to learn the entire mechanism. Me, myself, I don't even know it. The only thing that you have to know is that, first of all, we're gonna start by preserving that carbon chain. And at the end, you make the epoxide, that's always gonna happen in the carbons that form that double bond. So at the very end, we're gonna get rid of that double bond and we're gonna make two new bonds. Now, because it's a thin addition specifically, those two new bonds to that oxygen have to be on the same plane. So they can both be wedges or both dashes, okay? So again, main part, that's it. That's all you have to know. Double bond plus peroxy acid, thin epoxide. That's it. So far, questions on the first way on how to make epoxides? We're good? Pretty simple. It's just mostly memorizing stuff. Okay, now let's show the second way. Now, this is gonna be the reaction that we just talked about, the West reaction. Pretty simple. What are the two main steps for the West reaction?
Right, you need an alkyl halide.
You need an alkyl halide, what else? How do you know you're doing a West reaction? What are the elements that you see?
Strong base.
Strong base, alkyl halide, and what else? You have some sort of alcohol group, exactly. Those three main things point you to the West reaction. Now, in this case, again, because we're trying to form an epoxide, something that's cyclic, it has to be an intermolecular reaction. So in this case, first of all, let's start by writing the steps. So first, your acid-base reaction. And then second is your SN2 reaction. Now, in this case, your professor might give you another reaction before proceeding with the West reaction, which is actually going to be your halohydrin formation from chapter 8. So let's quickly review that one, just in case. So we have the double bond, the reagents for the halohydrin formation are always going to be some sort of halogen and water. Now, if we remember from Orgo 1,
Add
anti-addition, beautiful. So at the very end, we get rid of the double bond. And then instead, we're always going to end up with an alcohol group that came from the water, and then the halogen from the actual reagent, and they have to be trans to each other. That's the main part.
So if there's no H2O, it would just be two chlorines trans.
Exactly, yes.
So how does the chlorine leave as a leaving group?
Let's talk about that. So we have two of the main things that we need for a West reaction, alcohol and alkyl halide. What's the last aspect that I'm missing? What do I need?
A strong base.
A strong base of some sort, yes. So it can be NaOH, or in this case, I'm just going to show you another one, which is just sodium hydroxide. No, same process. That sodium goes away and you're left with your hydride ion, pretty strong base. So it's going to be taken away that hydrogen from the alcohol. And now I'm still preserving the stereochemistry. I didn't touch anything. So I have an O minus and I have my chlorine in here. Now, at this point, everything is within the same molecule. So nucleophilic attack from that oxygen. It goes to do the backside attack and that kicks out chlorine. So at the very end, you're going to end up with still a cyclic structure. And now we have our epoxide. And remember, SN2 flips the stereochemistry.
How'd you get that?
Using my real quick. With the lower end.
Yes. Okay, there we go. Let me get the pointer. Okay, so again, once we're at this point, that nucleophile attacks the carbon with a good leaving group. This is a backside attack because it's SN2. So we have to flip the stereochemistry. The bond from that oxygen, we didn't really touch it. It didn't get attacked. So that's why we're preserving it. And then the only bond I'm changing is the one with chlorine. And that's it. They both make the same thing, exactly. So yeah, you have to know those two ways on how to make epoxide. It's really important. Yes.
Could you, scroll to the,
Wait, why do you use NaH?
It can be any base. It doesn't have to be NaOH. It can be any base.
when you doing the halohydrin formation,
Mhm.
how does so originally you would have the two, without the H2O, like if you just have Cl2, you would have the two chlorines trans. to
And
each
you
other.
wouldn't be able to proceed with a West reaction.
But how, so is the intermediate, the two chlorines that are trans to each other, and then one of the chlorines gets kicked out by the OH? Like, how does that chlorine get switched with the,
So yes,
Wait.
after you form the transversion with the two chlorines, that water is gonna be attacking. I think this was a Markovnikov reaction. I don't remember correctly, but you would attack the more substituted carbon that has the chlorine. You do the backside attack, and that's how you kick out the chlorine.
So you're getting H2 as a byproduct in that base reaction.
Yes, which is just gonna be a gas. So
And
That's true.
also you said any base or any strong base?
any base, any base, specifically for Dr. Roche, it would be a strong base. But in general, just for this class, anyways. And again, this is the main product. Okay, so far, any questions? We're good? Okay, so technically I'm over time, but let's just quickly talk about how to break them, okay? Let's just quickly talk about them. I'm not gonna show you the actual mechanism yet. I'm gonna save that for next session. But like we learned, epoxides, they have a lot of ring strength, so they're gonna be very reactive in both acids and bases. So really quickly, what was the ranking for acid cleavage for normal ethers?
3, 1, 2?
3, 1, 2, beautiful. Now, for bases, it's gonna be slightly different. What do you think the ranking is gonna be?
1, 2, 3.
It's gonna be 1, 2, 3, exactly. And that's where we're gonna end off.
Why is it 1, 2, 3?
Yeah,
That just
Really?
makes
Do not ask me, I have no idea. At this point, like I made my peace with this. I just accept that ranking and that's it.
It just made sense in my head.
Yeah. So yeah, I stopped asking questions on the ranking because they confuse me more. So yeah,
So what's the question I could ask him in class for the, what?
if he shows you the how to break your ethers, normal ethers even,
So
the
what's
acid
rating
cleavage,
for ether cleavage,
for acid cleavage.
for acid cleavage in
Mhm.
ether?
And that's it. I'm gonna stay in the podium for a little bit to try to talk with him, but if he gets too late, I'm just gonna go to back. So yeah. But okay, technically we're almost done with the handout. We just have to do this last page and talk about crown ethers, which is actually pretty simple, which is counting. And then we have a few multi-step synthesis problems. So if you can, I would start trying to do them on your own.
Do them on our.
Yes, yes.
Spirit, okay,
Yeah,
I can do that.
what do you mean, how should we learned it already?
Okay.
The very first one, you're already there. You see the dots? That's already there. Now, the next two are dealing with breaking epoxy specifically, but again, the reaction is very similar to what we saw on breaking normal ether. So just give it a try. Give it a try, see what happens. You have all of the rankings, so just give it a try. Because if we have enough time to go over chapter 13, we're gonna start next session as well.
Yeah.
So yeah,
So next test is gonna be what, end of 12, 13, 14?
Yes, and maybe 15, I'm not sure. But 15 is not bad, and 14 is not bad either, so. Yes.
Actually gonna hold reviews, I heard he lies. He never does.
Okay, so Jay is a very busy person. He tries to help students always. before a couple of years ago, he did used to make reviews for you guys, but he announces that he's gonna make reviews for every semester, but sometimes he doesn't have the time. So most likely he's not gonna have reviews. So just keep that in mind. But I'm gonna try to make reviews for you guys instead. So
That's exactly.